Hello everyone. I just wanted to make a video about allosteric modification as one of three enzyme regulation types or ways of doing it. So anyway, just do this real quick. So here we have my representation of an enzyme here, and on this enzyme we have the so-called allosteric site as well as the enzyme's active site. Okay, so as you can see here, I tried to represent just the allosteric site. It's a little bit more, maybe kind of triangular. Here it's more of a rectangle type shape, which aligns with our substrate, which is also a rectangle, which it will bind at this domain of the protein, aka the enzyme. And I also added here just some ATP, just because many of our reactions that we talk about include ATP, but it's not really that important here. And as a product, let's just say we get something like this circle, doesn't matter, whatever. As our product for this reaction, as our end product plus let's just say ADP. And now, for the sake of this argument about talking about allosteric modification, how do we modify this enzyme here? Well, let's just say, okay, downstream from this reaction, we have another reaction that I will not show, but just our product. Let's say our end product here from the entire pathway process is like this. All right. And we get a bunch of these at the end here. Sorry, I'm not consistent with the shape, the way it looks, but whatever. Okay, so we get a bunch of these. For whatever reason, we have an excess production of this end product. Question is, how does this affect this pathway? As we talked about, allosteric modification is heavily based on the concentration of some reactant. Typically, if it is an end product of that, or I would say downstream from that, that rate limiting step reaction. I'm sorry. So this is the rate limiting step here, meaning that this, by way of this reaction, we can control the rate of this process, the overall process. We can limit the amount of product that comes about. So here we have more substrate, or not substrate, end product than we actually need. So what we'll do is bind to this allosteric site on our original, this first rate limiting enzyme. And as a result, let's just say for learning purposes, that this leads to a conformational shape change of this enzyme, such that its active site changes its shape and thus has much difficulty in reacting with its original substrate. See that? Okay, that's just my representation of it, just to show that this shape change causes limitations in the enzyme's activity. Thus, we have allosterically modified this enzyme. So I hope that helps a little bit, a lot of bit, and I'll see you for the next one. Bye. Hello again. So here we have covalent modification, also known as covalent regulation. Keep it brief. Now I've shown here we have one enzyme, so it's really the same enzyme. this we'll call is the active enzyme, or active form of it. Here is the inactive form of this enzyme. Okay, now at the top here, we see the insulin receptor. So insulin being a hormone, this is just my representation of the insulin hormone, even though it doesn't look like this, but whatever. And here is glucagon, which is the opposing, in terms of its action, hormone to insulin. And here we see their receptors on the plasma membrane. Okay, so they call the receptors to modify or allow the cell to react to its changes in its environment. That being these ligands known as these hormones, endocrine hormones. All right. So anyway, through a cascade of events, through signaling, signal transduction, so a cascade of events within the cell that occur, we have something called, let's say, it's going to be a kinase and a phosphatase. So here we have, let's say, protein kinase. So this kinase is going to use phosphate group, can be donated from ATP, and will then take the phosphate group and add it to the enzyme. So the enzyme basically ends up, so let's see that. Yeah. With the addition of a phosphate group, and then in this case, it will activate, turn on, it's like an on switch for this enzyme. Thus, it's able to increase activity or act at all. Now, the other side of this, and this gives us ADP. The other side of the coin, we have a protein phosphatase. And this is why I want you guys to understand, the phosphatases and the kinases, and because they're so important. So this phosphatase, it will use water in some way, eventually. So, H2O. And let's just say here that this enzyme already had been phosphorylated. Okay, let's say that it was already. So it was sorry. So to show it here, it would be active. Here we're going to inactivate it by using a protein phosphatase. So right here, okay. And through process of hydrolysis, we cleave off, cut that off, and thus we end up getting an inactive enzyme. So it's back to square one without being phosphorylated. So that's really it. Now, whether that enzyme is active when phosphorylated or dephosphorylated, it really just depends. Most reactions, they tend to be, it's active when it's phosphorylated, but there are several that are also the enzyme is inactive when it's phosphorylated. So, and either action could come from the kinase or the phosphatase. But anyway, this is how it works. This is covalent modification. Hope this helps. Have a great day.